Okay, welcome back. It seems like people survived, apart from a few annoying glitches in the edX submissions. People sort of survived and mostly got the software installed. And seems, I mean, if there's questions that or there's problems that I didn't hear about, then let us hear them right after the class. But it seems like things went fairly smoothly, considering. And I think it's great to use the discussion forum, so you'll get a probably get a faster answer if you use the discussion forums. It's great for us because then we answer the questions once, and you guys can answer your own questions. But a few people have had sort of specific questions about Drake, and you can feel free to post that on the discussion. Or some of them I've moved to the GitHub forums just because they're questions that everybody will benefit from the answers to. So thank you for using those tools. And feel free to, we're going to try to put little questions at the end, sort of survey questions at the end of every problem set, because that was really interesting to see your feedback already, and that's just that's very, very valuable to us to get your, hot off the presses, I'm annoyed at something or I'm not annoyed at something feedback. Is really, really good for us. Okay, so we did dynamic programming last time, and let me just put up a few of the details that we did last time because we're going to build on them this time. So, I got to calibrate my pen. Sorry. What the heck? All right. Okay, so last time we did dynamic programming. We motivated it with the double integrator, right? So let's just remember real quick what we figured out there, which was if we had this second order system with constraints on the input, right? And I sort of like to think about that as a mass, just because I don't know, I guess I like mass. I like things that move and have inertia and everything, right? So some brick that's trying to get from its current position and velocity to some 0 point as fast as possible, typically. And we figured out that for the minimum time problem, although we didn't prove before, but we said the optimal control was this bang-bang policy. Hit the accelerator, then hit the brakes, right? Bang-bang is a formal term from control. I didn't make that up. I would have if I could have. And we remember we had solved the sort of Q equals Q dot squared. It was this magic surface where that was where you hit the brakes. Same thing on the other side, right? And that over here, we always did that. And on the other side, we always did this. This was our U equals -1, or hit the brakes. And then this was our, hit the accelerator. Right? That was our solution. And then the other thing we did was, after deriving that sort of from first principles, just thinking about the physics of it, we did it again numerically, right? So we gave a numerical algorithm. Based on the idea of graph search. Which we called the value iteration algorithm. And that one worked by having some estimate, j hat. I always use these hats to mean estimate. That's what the hat means. Of being in state Si is somehow the min over A. Right, so this J is a cost to go, or an estimate thereof. And this equation, really, you should just read as saying that the cost to go of being in state Si is the one-step cost of being in Si and taking the best possible action, plus the cost to go from the next state, right? So if I'm working towards the goal here, then the best score I can possibly get here is the best score I could possibly get here plus the cost to get there, right? And there's multiple places I could get to, so I'm going to take the very best. So every time I go back, it's going to be the cost from the next state. That was my dynamics, right? Sn plus 1 was f of Sn A, right? And this was my one-step cost. That was my edge cost. This was my G, if you will. And then, so I'm going to say that I'm going to get here, and then it's the cost to go from here plus the cost it took me to get there. That's what this equation is. Extremely easy to remember, right? As long as you understand where it's coming from. Otherwise, it's just a bunch of symbols. Okay, so we got this this equation. We said there was this really nice property that j hat converged to j, right? So if I made this a vector, a set of values, one for every state in the discrete state sense, right? If I tiled my space with, if I approximated this with a bunch of discrete states, and I turn this into a graph approximation of the true dynamics, and I figured out the cost to go from every one of those nodes by just running this algorithm. Then even if I just made a random initial guess at that cost to go, if I just run this algorithm over and over again, then that initial guess will converge to the true cost to go, right? And we got out, boom, the value function, the cost to go function that we expected to see for this, and we ended up getting the policy out, which we can always read the policy, right? Once you have your estimate j hat, or if you have the true j hat, then the best thing you can do is take the action which gets you to the best next state, right? So my U star, or my A star here, my best action is the minimizer over A, arg min over A. It's the A that minimizes this function, which was G Si A. It's the exact same function. J hat star F Si A. Right, so people get that? Is that you'll get to do that more on the problem set, but I know the problems that you were thinking about last time didn't yet have DP. So if I know the cost to go from any state, then I always know what the best action is. I'm going to take the action that gets me to the best state in one step, right? Okay, and so that gave me back those plots that look just like this policy. Awesome. So, I mean, when I first started playing with these things, I got really, really excited. I thought, graph search can understand my dynamical systems, right? And it's exciting to see that such a simple algorithm can can really penetrate the long-term dynamics of these very complex systems, potentially. Okay? But then as you start really playing with it and trying to push it and trying to make real systems work with it, you're going to start getting a little frustrated. Okay? Because the discretization stinks. It really screws things up and mucks things up. And we'll ask you a problem this time that if you discretize it a little wrong, like maybe there's ways that you'll discretize it wrong without giving the answer here, but where the solution doesn't even necessarily converge, right? And if you discretize it too coarsely, the solution might look nothing like the real solution. Or and we had to do that little flub to approximate the fact that the one-step dynamics don't actually land directly in one of the other cells that we discretized. There's all this junk in there, right? We like continuous systems in this class. We like dynamics. We like the continuous differential equations, smooth trajectories, all these beautiful things. Can we salvage this algorithm, take this sort of beautiful idea of graph search that works great for discrete systems and make it do something magical for continuous systems? Okay, so that's the goal for today, is to take the same machinery, clean it up, and make it work more naturally than we did the first time for the continuous systems. Okay? Now, there's a couple goals for that. There's a couple reasons to do that. One is to actually just give you better algorithms that you can actually implement. Another motivation is that you'll be able to do some analytical optimal control with it in limited cases for simpler systems. But even seeing those systems, you'll be able to, it'll improve your intuition, I think, about the optimal control problem. So there's a lot of value in that. And I think there's lots of good reasons to do it. Okay. So, sure.
Are you trying to make a distinction between arg minimum and minimum? Or are they the same thing?
They are very related. The minimum, if I say minimum of this, that returns the value that is the minimum value of that. If I search over all A, what's the lowest value of this function that comes out? Argmin says if I search over all A, what's the value of A which made the minimum function come out? That's the difference between argmin and min, yeah? So the value that comes out is J, and the thing that minimized it is the action you want to take. Yeah? Great, thanks for asking. Okay, so one point to make before we make these equations more continuous is that this equation that you see before you here, these two equations really, we've talked about them as this is the algorithm. This is the value iteration algorithm, okay? But you could also think about them in a slightly different way. They're also, I don't want to say it's a theorem, but they're a condition for optimality, okay? So for instance, you can run this and get something out that will converge to the optimal cost to go. But you can also treat this as a test, right? If I walk up to you and you say, look at my robot, it's optimal, right? And we have a little discourse, and you say, I say, prove it. You convince me that your robot is optimal. All you have to do is give me a J, okay? I'll do my homework. I'll plug it into the equation here. If that J satisfies this equation down here, then I'll be convinced that it's optimal. And if your controller A satisfies that equation there, right? I don't have to actually run the optimization algorithm to do it. If you give me a J which satisfies this, that on the left-hand side equals the right-hand side, yeah, then I'm going to believe you that it's optimal, right? You've convinced me. This is a check for optimality, and it's sort of the same as saying the algorithm that as J hat converges to J, this algorithm will stop doing anything because those two are equal, yeah. Right. So when you found the optimal policy, that means that every time I update this, I'm going to get the same answer again. I'm always going to go to the next same state, and the cost to go has converged to the true cost to go. And so I can use this as a check for optimality in addition to an algorithm. Okay. Now I wanted to say that because as we go to things that are more continuous, sometimes it's not going to be an algorithm, but it's still going to be useful as a check for optimality and a proof of optimality. Okay. In the continuous case, some things will be exactly algorithms, and some things will be sufficiency theorems. Okay, let's do it. So, wrong button. So, All right, so let's be clear here. When we made that graph approximation, we took our beautiful continuous state, continuous action, continuous time system, and we discretized it in every possible way, right? So we really last time we discretized state, right? We took our continuous x, which maybe lives in some space big X, and we turned it into some finite alphabet of states S, right? We turned our continuous Q and Q dot into a bunch of, it had to live in some discrete cell in our graph. We discretized our actions in the same way, right? We said we took our U and we turned it into some discrete alphabet. And I used a different letter, A for that, actions, instead of the control input U. Okay? And we discretized time. Right? So we took our, we ended up going from our x dot equals f of x u formulation over to this Sn plus 1 equals f of Sn A. So if we're going to get back to the place we want to be, we're going to have to address all of those in order. Okay? Probably in a slightly different order. That's the recipe for today. That's the plan for today, is to march through those and understand the implications of getting back to continuous in each of those different ways. Okay, so let's do discrete state to continuous state first. We sort of have to, because it doesn't make sense to have a continuous time system on a discrete state. Okay, so or it would be harder to do that. Okay, so let's think about doing this first. Let's take the discrete state and turn it to continuous state. So, right, our update, which I'll just write again since it's lost. We basically said for all I, we're going to run this update. Okay, so now I want to go from S to X. Okay, let's do it. So for all X, J hat X. That wasn't too bad. Okay, there's a little more to it than that, but that's the first step, right? Is that there's really algebraically there's nothing wrong with writing that down again over some continuous state, right? The problem is that doesn't actually give me an algorithm, right? Because how do I represent a continuous function x? And how do I do this sort of mapping from an arbitrary continuous function here onto, I need to write some new arbitrary continuous function, right? So computers aren't good at that. I need to somehow come up with a set of numbers to represent this, and a finite set of numbers would be good if I wanted to be representable in MATLAB or on my computer in general, right? So somehow there's more to it than this if I want to make an algorithm out of it. I need to come up with a finite parameterization of this. Does that make sense? This J, I want you to absolutely be crystal clear the fact that J is a scalar function, right? That there's something sort of magical about that. F of x is a vector valued function. If you give me a state and a control, I'll give you a derivative, right? This It's a vector valued function. But somehow the optimal thing I need to figure out is just a vector valued function. It's just, sorry, is a scalar value, is a scalar function over state. So, it seems very plausible that I could represent this as a function over state. I just need to pick how. And I need to think about the implications of somehow doing this update when I have now a finite parameterization of that. It's not just a technical implementation detail. This is fundamental about whether this algorithm is going to work, right? Once we have now a finite parameterization of this, there's really big questions about, how do we actually implement this update, right? Does it converge? These things are all going to come into question when we've somehow got, a function here instead of a discrete set of numbers. Okay, so to tell you that story, I need to make sure you understand the basic idea of function approximation. Okay, so if you're coming from the machine learning side of things, then you know function approximation well. We're not going to do hard function approximation here, but we need to somehow think about how to take this function, which we can evaluate if we've got a representation of J, and somehow represent it in this update using the idea of function approximation. So to some extent, this is an aside on function approximation, but it's central to what we're going to be doing here. All right, so the idea is we need to somehow, we want to write down a function with a finite parameterization. Let's call it P of x. All right, so there's lots of different choices. There's lots of different ways you could do that. You could write it down as a polynomial, right? You could say P of x is but to some finite number, right? You can write it down. Remember our neural network example that the people use neural networks for function approximation all the time. We had this notion of a sigmoid in here. I didn't really tell you too much about it except for the fact that people think about neurons possibly as represented with these tanh functions. So you could write something like that down. People do write these sort of tanh of, let's say, alpha times x as another way to do function approximation. And if you had a whole network of these neurons, that would be a more general set of functions you could represent. Right? But there's lots of different examples of what you could represent here. And the big idea here is that we're going to have to use the machinery of function approximation to make this update, right? So what we want when we see this update, j hat star of x, and I want to set that function to be now the right-hand side. My shorthand, okay? Right, I want to somehow take this left-hand side and make it as equal, as close as possible to this, right? So I need to somehow pick my representation, and then every time I do this, what I'm going to be doing is setting the parameters here. In both of these cases, I've written them with the parameter vector alpha. I'm really going to be setting alpha to make this function look as much like this function as I can, right? Ideally, like we're going to use it the least squares sense, right? So, make these equal in the least. We're going to try to find an alpha that makes this equal in the least, as close as possible. In the least squares sense. meaning I want the difference of the function evaluated squared to be somehow small. Okay, and to be very explicit, when I'm using an approximator parameterized by alpha to describe these functions, I'll write a little alpha down here just to make sure we remember it. Okay, I'll call these J evaluated at alpha. And so this update, this idea of somehow making this update now happen at the function level using function approximation instead of using just setting a vector here, this is often called fitted value iteration. Okay, and there's lots of people that talk about this in the community, or so there's lots and lots you could read about this if you like, and I'll tell you some of the key results when it's time. But when you're doing this fitted value iteration, and when you're trying to do this sort of this setting of the new function, there's some choices here that you can make up here about what your representation is that can make this operation a heck of a lot easier and can give you stronger understanding of what's going to happen in that mapping. Okay, so in particular, a really important class of functions is the linear function approximators, the linearly parameterized function approximators. So this actually is a linear function approximator. Even though it's a nonlinear function of x, it's a linear function of the parameters alpha, right? So that means that's going to make all the difference. If I want to set this at a bunch of x's, I can actually set this very easily. I can find the alphas very easily. So I'll write if I choose my j hat star alpha of x to be represented as some combination of potentially nonlinear basis functions, then life's going to be better for us. Just that for me, actually, that's not a huge loss in representational capability because this can be polynomials, this can be radial basis functions. I'll show you a few examples of what these can be. This can be very general, really. And all we're asking is that the alpha be outside of the nonlinearity, right? So the tanh case didn't work. The tanh had an alpha inside the nonlinearity. But a lot of them we care about will work, and that's okay. And I'll write this often in the vector form too, okay? So let me see if I can sort of help, I can pull up a simulation here and just a little demo to help you understand sort of the way that you go about using these linear function approximators, okay? So all right, so let's say I have some function that I want to approximate. Okay, so I made some nonlinear function, sine x squared plus tan x, just some sort of crazy, interesting, highly decimated, highly pixelated function up there. Okay, but now I want to somehow fit it with a library of these, with a linear combination of potentially nonlinear basis functions, right? So this is the standard picture you should have in your head, right? So I'll take a bunch of, let's say, noisy samples of that even. So if I'll take, the way I did this is I just said I'm going to pick a random value, pick a random x value, make a y value that's the true function plus a little noise. Just so let's say I get noisy evaluations of that function, okay? And now I'm going to take a bunch of nonlinear basis functions. These are the radial basis functions, okay? And I'm going to try to find a linear combination of these nonlinear basis functions that matches the data as well as possible, and the hope is that that'll match the original function as well as possible, right? So it turns out because it's linear in the parameters, I can just solve a least squares problem. I can literally just call backslash in MATLAB, okay? And I get a bunch of scalings of that. It says you should use, you know, this much of that one and this much of that one and negative of that one, okay? And then you sum them all together and it's, you know, it works really well, right? So then you get, this is now the approximated function for that, right? Given the data, using just as a linear combination of these nonlinear basis functions. Does that make sense? And that's a one-shot closed form. You know, given the data, that's a one form. That's just a least squares. You know, you can see the code here. All this is just setting up the bases, and then oh yeah, it's right here. I did it myself. I don't even know why I didn't just call backslash. So it's just a closed form solution to the fit. Okay. So, and you could do a lot of different basis functions, right? So there's a rich thing. So here's a, you know, I could have used sort of sine wave basis if I wanted to, right? So here's a, I could call it Fourier, but this is just the real components of it, right? So I get these crazy coefficients, but it'll still fit pretty well, right? And I could use the polynomial basis, right? So crazy polynomials, crazy coefficients, but that one didn't do so well, but I was stupidly chosen. That's why it had 2 comments. Ah, that was like, don't use that one. Okay, that's what I see. Right. All right, got to remember that. Okay, and then, well, let me actually, so the thing we did, the linear interpolation we did last time fits in this framework too, but maybe before I show you that, let me just make sure you can guess what that's going to look like. So what does a linear approximation, linear interpolation look like in the linear function approximator case, right? So last time when I approximated my update as some combination of the neighboring cells, right? I said I landed here, so I'm going to approximate it as a little bit of this cell, a little bit of this cell, a little bit of this cell. That was just doing linear interpolation, right? So you could think of that as if I had, you know, a bunch of numbers like this, and the value 1 here, or let's call it alpha 1, alpha 2, alpha 3, right? And then I want to just smoothly interpolate between those different points. I want my function approximator to just be the linear interpolation between those points. So if I ask you for a point, the value of a point x, what I'm going to give you back is my function p of x is going to be, in this case, I want it to be 2 minus x times alpha 1 plus x minus 1 times alpha 2. Is that right? A little bit of alpha 1 and a little bit of alpha 2, right? And I'll get this sort of this smooth interpolation out, right? Okay, so that's linear interpolation. You've done that a bunch of times. You call it first order hold, call it whatever you want. Okay, you've done that a bunch of times. What does that look like in the function? Like if I wanted to write that as a linear function approximator, what does that look like? What would my fees look like for the linear interpolation case? Can you think about that? Is that? Yeah.
It'd be like triangles, scale.
Awesome. So the interpolators would be just these triangles. Use my color palette here. Right? It would be triangles that look like this, and then alpha would scale them. Exactly right. So that's what the barycentric interpolation looks like. If I uncomment that. Right, so I get my triangles. That's my linear interpolation of these things, and then I try to fit just the heights of those different triangles, right? I get this, and I can get my piecewise linear approximation of the data back out. Okay, so that's just a tool that we have, that if we have linear function approximators, you give me a bunch of points that I want to fit, I can fit them as well as possible with a closed form solution, just using least squares optimization. Okay, so that's a tool that we're going to use in the value iteration update next. Okay. Does that make sense? function approximation? Yes? Cool. You'll use it in lots of different places. All right. So, so if we did, for instance, use that just to make that close that story here. So if we did, we did use these triangles to do the interpolation, right? The barycentric interpolation I talked about that you saw in you might have seen in the code if you looked at it. The barycentric interpolation that we did was just the linear. It's just a generalization of the linear interpolation to n dimensions. Okay, so that's just what the barycentric interpolators do, and there's different ways to do them. I chose the one that's on a triangulated mesh. Okay, and also just to make sure we connect the dots. We can write that. Remember how I said last time that we wrote this stochastic update, right? We wrote this. We said I said you could approximate. You could do the interpolation a little better by writing down this expected cost to go, right? This J star SI is the min over A, and then I did an expected value here, so G SI A plus sum over J probability of Sj given Si, right, times J Sj. And that was my stochastic update, my stochastic shortest path. So for the barycentric interpolation, I'll make that connection sort of clear now, right? That at the grid points for barycentric, the J where X is at mesh point I just equals alpha I, right? So at some mesh point, I just get the value alpha back. So really, this thing here is exactly the same as my interpolants times alpha j, sum over j. And so the coefficients of the linear interpolants here were exactly what I treated as my transition probabilities. So if you just work that through, the update is exactly analogous. That's why I said that there was this nice duality between the stochastic shortest path problems and the linear interpolated function approximation that we're doing today. Okay? In this special case of barycentric interpolation, it can be treated exactly as a shortest path problem, where the coefficients are just like you could treat it as transition probabilities. They fall into the equations in exactly the same way. Okay, so so now that the challenge is to say if I'm going to use least squares function approximation to do this map, right? So I'm going to somehow say at a bunch of points I'll say for a bunch of sample points I. I'll just take a bunch of random points in my state, and at those places, I'd like for this to hold. I feel like I write the same equation a bunch of times here, but I can make this work by just saying I want this to be approximately my least squares. I want to do this the same way I did in MATLAB. I get a bunch of points here. I've evaluated. At xi, I have a desired value here, which is this side. And I'll just have my linear approximation. I'm going to minimize over alpha some least squares problem. The value I've gotten here, which is right? Sum over all my points. And my claim is that just because this alpha enters linearly here, I can just solve this away with a backslash operator in MATLAB. And what I'm going to get is something that, like you saw, depending on the basis I chose, it should fit this desired function fairly well. It'll never fit it perfectly. Again, if it was exactly in the same function class, it might fit it perfectly. But there's a bunch of questions you should ask now, right? You should say, okay, so what happens now if I mean, it might be that this function here, this desired value, this desired set of points, is not even representable with the sine waves I chose or the polynomials I chose or whatever, right? It could be that there's just a lack, that there's not even any alphas I could choose that would make that fit exactly. That's certainly possible, right? It's probable, I would say. And then if I do incur error here and I start iterating, then what's going to happen, right? Is this actually still going to converge? And the high order bit really is, the news is not too good, honestly. So, the high order bit is that you can come up with really simple examples of things where actually the result of this is in the function class here, and that update actually still diverges to infinity. That you'll get just stupid results coming out, right? So in general, it's not, even for linear function approximators, that update is not guaranteed to converge. This update might not stop ever, right? And even if it did converge, we could only sort of hope for this to converge to the best approximation in the class of functions I'm representing to the true value function, right? Even if it did work, but it's not guaranteed to do that. There's some special cases where they are. And I'll give you some of the references to those in the notes to make sure you have them. But the higher order bit really is that these things get bad fast. So that sort of hits the brakes for some people, right? That some people stop using them there. I'd say the machine learning crowd has been more bold, and they just say, I don't care if I have a proof; it still works well a lot of times. And in fact, you can get some spectacular results using that sort of an update with function approximation. Well, one of the earliest results was the backgammon playing, TD gammon. There was a guy, Jared Tesaro, that basically made a backgammon playing algorithm. It played against itself all the time, used function approximation to represent the optimal cost to go in little neural networks, and came up with a backgammon playing program that could beat the world masters at backgammon, right? So I don't play backgammon. I don't really know how good that is, but it sounded pretty impressive to me. And it was done with when computers were pretty slow, and that was a big time result for the field, right? And they've gone on to do other games too, and now the reinforcement learning world has conquered a bunch of the hard games. They even do well at Go these days. So okay, so it's not guaranteed to converge, but in practice, some of these can work very, very well. All right, so and we'll have times where you'll be able to think about actually implementing that and understand some of the details of that. But the high level bit is that we can change the s's to an x. The algebra doesn't change. The conditions that you have to check for if you want to convince me that it's optimal, the conditions I check are almost identical. I have to check them potentially for all x. But if I'm going to make an algorithm, then I'm going to make a finite parameterization of my function and check and update it potentially just at sample points I, right? Okay, so but given those caveats, we've made the leap to continuous state spaces. Okay, so now let's do continuous time. Okay. Yeah.
Another question. Sure. So an alpha represents the weight, represent the weights of the basis function.
Yes.
They all represent the weights, the probabilities of the weights.
So in the barycentric case, then you should think of the alphas as being the value of the objective at the mesh points, of the cost to go at the mesh points, and the weights of the interpolant, which is the probabilities, are the coefficient, are the actual.
Sure. How does that relate to that being the weights of the basis function?
So the way I thought about the stochastic graph is I say if I land here, I'm gonna take the probability that I was in each of these nodes. Yeah. So the expected value of that is equivalent to saying I'm going to interpolate the value at each of those nodes. So the value of each of those nodes is alpha 1, alpha 2, alpha 3, and the coefficient, the probability of being in each of them is my psi. Yep. Yep. So that's the match. Okay. So how do I go from xn plus 1 now to x dot time? What are the implications in the value function update for this? Okay, so let's take this value function update and take it and try to see if we can see what happens if we were to basically intuitively make the update time step extremely small. We'll take the limit as the update goes to a dt of 0. So what I want to do now is approximate this with a time step dt. Okay, so I'm going to take this and approximate it like this. Okay, stick it into my equation here. I'm going to take a limit as dt goes to 0, right? And also my g of xa here, I'm going to think of this as the integral over some dt interval, g of xa. Okay, and I'm going to take the limit of this as it goes to dt goes to 0. Okay, so to first order, that's going to look like this. I'm going to take the limit as dt goes to 0 of g of xa times dt plus j at x plus partial j partial x f of x. You can think of this as partial j partial x. This is x dot, which is partial x partial t times dt. Okay. Still need my min over a. And I'm going to take the limit of that as dt goes to 0. And I apologize that this tablet makes my handwriting look like a 5-year-old. I do have a 5-year-old at home, so I can say it's about a 5-year-old level. But okay, is that clear enough? Yeah.
When you're iterating, you're taking the time step to 0 out there. Like xn plus 1 is that xn plus dt.
Oh, thank you. Yes, thank you. Good catch. Yeah, good catch. Okay. Now let's see what we can do about this, about simplifying this equation and taking that limit. Okay. So the j of x here doesn't depend on dt and doesn't depend on a. I can actually pull that all the way out. And in fact, when I do pull it all the way out, what we see is that it was already on the left-hand side. So this guy actually just will disappear, and I get a 0 over here. Okay. My dt I can actually pull out. It doesn't affect my min over a if I multiply by a dt. I can actually pull my dt out and just take it to the other side, divide it by 0 by dt, and my dt actually just disappears. Since everything in here is multiplied by dt, it doesn't affect my min over a here. I can pull it out, and then my concerns about taking that limit disappear, and I end up with this as sort of my defining equation. Okay, so this, we have to think about whether this makes sense as an update, because I've lost my left-hand side. We can talk about that, okay? But what I first want you to think about is this is a condition for optimality, okay? So if I'm going to take your j now, and you're going to try to convince me that it's optimal, all I have to do is look at its derivative now. This is a partial differential equation. It's defined based on the derivative. Well, it's just a part. This is just a derivative equation. Yeah. So all I have to do is look at the derivatives of j, and if this equation is satisfied for the minimizing a equals 0 on the other side, then you've convinced me that it's optimal. Okay. So it's really interesting, actually. This is actually much cleaner in my view than the discrete time case, where I had to somehow apply the update, interpolate to the next state, figure out where I was in the next state. Now it's a point-wise operation. I can just look at all my x's. If at every x, partial j, partial x, f of xa, here evaluated just at x, if this thing works out to equal 0, then I'm good. It becomes an easier thing to check in some sense.
How do you know if j is a smooth function?
So we're going to have to, so this is only going to convince me if j is a smooth function, and that's defined everywhere, right? There are times where j won't be a smooth function, and we'll have to use more sophisticated things. Good point. Yeah?
So what is the meaning of g now? Is it the cost per second of executing a certain action while you're at point x?
It's still the cost to go, but it's now a continuous integral, right? So now j is defined as
G.
oh g. Oh yeah, good. Yeah, it's the instantaneous cost, which so this is the relationship. Yeah. Right. Yeah.
But we only know like what j actually is kind of when we're done with everything. So how can we calculate UJDX?
So again, if you give me a j, you'll convince me that it's optimal if it passes this test. But this is also going to give us a means to get j. Yeah. Okay. So this is actually, in some sense, much more beautiful than the previous equations. And in some sense, potentially easier to work with. I don't have to do any integrals or anything here. I can just do point-wise evaluations, point-wise check. And this is going to be the means by which we derive some values of j. All right, so let's do an example here. So, all right, so let's think about this in terms of, so right now I'm still in this murky middle ground where I've got a discrete action space, but now I've got a continuous time differential equation and a continuous state differential equation. Now, so the one place we've managed to sort of end up with a discrete action space being okay is that min-time double integrator, where it either did u equals -1, u equals 1, or u equals 0. So let's just see if we can convince ourselves by this, if this optimal policy that we wrote down passes this check. Yeah? All right, so what was j for the minimum time double integrator problem? What was the value of j for a given, it's some function of x? What does that value intuitively correspond to? What is the cost to go for the minimum time double integrator problem? If I'm in some function x,
Time to reach the goal.
it's the time till it reaches the goal, right? Say in seconds. Now you remember our solutions were this, our controller was this discontinuous thing. And our solutions went wham onto this and then rode the wave down, right? And this is the same thing on this side. So I go boom onto this and then ride the wave in. All right, so we're going to write down, it's not hard to derive it, but I'll just write down the equation for what the total time is. But intuitively, the way you'd solve for it is it's the time it's the time of this action, time it takes you to get to this action. Plus the time that it takes to go along the breaking manifold, right? And if you start on the manifold, then it's just the time to get there. And because the dynamics of this were so simple, the time that you're actually breaking, let's call this the time that you actually reach here. We'll call that time at the manifold, Tm. Will be the event, the time that you reach that point. The time along it just equals q dot at the point you collided, right? Because q dot at t equals negative t. So if I'm waiting for, when is q dot going to equal 0? Well, when time equals the initial velocity. So it's literally just the time that you reach the goal. The velocity of the object when you reach the goal that'll be the amount of time you left to get to the goal. Okay. So certainly it's a smooth function as I go out here. That time will just go up. It takes me more and more time as I go here. It's just with my velocity. This is addressing your question then. So is the time to go going to be a smooth function? The policy is definitely not smooth, right? I go from here doing one thing to here doing completely a different thing. But is the time to go, the cost to go, going to be smooth? It actually is, right? If I cross this boundary, right? So I get the time it takes me to go here is that time plus this time. The time it gets me to go here is if I go incrementally off this trajectory, I go incrementally past this, and I take an incremental cost here. It actually is still smooth, right? So the cost to go is actually going to be a smooth function here. Okay, and it turns out you can write it down. So, for the u equals in this quadrant here, I'll write it down on the next page here. Okay. It's easy to solve just from looking at those equations, but you come out with something that's a little bit gross. Okay, and it's an easy exercise to see that this will actually satisfy that check for optimality I was asking you for, right? So just to make sure you're thinking about it, I'll do it quickly. You don't feel like you have to write this all down. It'll be in the notes, right? So if I take the partial derivative of that, I get a negative of this thing, 1/2 q dot squared minus minus q to the negative 1/2, right? I'll take the other partial derivative. Same thing, but now positive 1/2 q dot squared plus q squared minus 1. If I write the equations, check for optimality, min over a is in my finite alphabet here. It's drawn from -1, 0, or 1. My cost function, remember, was just 1 unless I'm at the goal. Okay. If you inspect this for the region where the u equals 1 is valid, this number is always going to be less than 1. Turns out it's easy to see, actually, that the minimizing value of a for this is going to be yeah. Thank you. That's what I am. So if I try to, because of the magnitude of this here, a equals 1 is always going to be my minimizing value. And if you insert 1 into this and you just solve this out, so that's why Michael pointed that out, then this thing here cancels this guy, the 1 cancels the 1, and I get this thing equals 0. That whole thing equals 0. So it passes my check in this space for optimality, right? If you give me this, magically give me this, then I can satisfy the equation and check for optimality. Yeah? I just did it in one quadrant, but it's easy to do. Okay, so the big thing that I want you to understand here is that something dramatic happened when we went from discrete time to continuous time. We stopped thinking about an update dynamical system and evaluating at the xn plus 1. We're able to turn it into a derivative condition on my cost to go function. Okay, this is actually going to make the analytics cleaner and beautiful, and it's going to give us some of the analytical results that you might already be using in your on your robots. Okay, and it turns out it's easy, the machinery is pretty easy to check too. Okay, so the key idea is that the dp has partial equations in it. Okay, partial derivatives. All right, so let's take the last step. How can we possibly get rid of this min over a? So if I actually wanted to do this as an update, what I'd have to do is check every a and make sure that make sure I know what's the smallest value of this for every a. Is there any hope of doing better? Right? Is there any? If this becomes a continuous u, when can I possibly do better? And actually solve this minimum with a numerical algorithm potentially. For a continuous u, right? If it's continuous, I need to somehow have a method that's better than checking for every possible u to make the jump to the continuous. All right. Well, in this case, we could have seen that if a was limited, we could just look at the sign of this and figure out what a was going to do to minimize this. There's a few key places where I can actually solve for this minimum analytically and get rid of it. Okay. And so that's the last trick I'm going to show you here, is a way that in many cases we can come up with algorithms that get around a discrete check of every possible action by solving this away in closed form. And it actually works for a pretty large class of systems. Okay. So let's think about this equation here. Now I'm going to turn it into a u. I'm going to write the equation that I want to get to is this minimizing the instantaneous cost on continuous state, continuous action, plus the partial derivative, f of xu here. The question is, when can I hope to solve away this minimizer analytically? Okay. Well, one of the things we said in the very first lecture was that a lot of times this has more structure than just f of xu. A lot of times we have control affine. I can write it like this, right? All the mechanical systems we care about, basically, are going to be control affine. That's going to help a lot. All right. And this cost here is actually, that's something we got to pick. So if we're willing to restrict ourselves a little bit, we can make this cost easy enough that we can solve it away. So let's restrict this cost a little bit. There's a few places you can, few things you can handle. The one I'll look at here is if I were to write this as g1 of x plus, I'll do 1/2 u transpose ru. So if I'm going to just have a quadratic cost on u, and then an arbitrary nonlinear cost on g. Okay, so if I have this, then now you can see what's happening here is that this function suddenly becomes an easy function in u, right? This whole function here is just quadratic in u. I need to find the minimum value of some quadratic function in u. I can do that. We can take the minimal value of a quadratic function, right? We'll just do that by taking the gradient of that function and looking for the place where it equals 0. Yeah, to try to find the u which minimizes this. Is that fair? This whole thing becomes just a quadratic function in u. I feel like people aren't happy with that. Are you happy because it feels like this is restrictive? Unhappy because it's restrictive? Or are you unhappy because you have no idea what I'm talking about? Are you unhappy because you don't want to take the derivative? Talk to me. What doesn't make sense about what I'm saying here? All right. I'll carry on. So this thing now, it's complicated. It's a complicated function of x. This is a multidimensional thing, but for any x, you give me an x, I can tell you I can minimize it with respect to u because it's just quadratic. Okay? It's a quadratic function in over u. Right? So I'm just going to take the gradient, find out where it equals 0. That's going to be my it's not only it's a positive quadratic function because I'm going to choose r here. I'm going to restrict my choice of r to be strictly greater than 0, and I'll make it even symmetric. That's strictly greater than 0. I'll make it a nice, easy function. Turns out you're going to be pretty happy picking those. That's really not a big restriction in my view. Okay? All right, and what you get out of it is really pretty beautiful. And it's really what I want you to understand about continuous optimal control. So let's take the gradient of this function with respect to u. I'll take the gradient of everything that's in the brackets there with respect to u. Should I write it out? Let me write it out first, just to make sure you have it all in one place. Okay, so I'm now I want to find the minimizer over u of something that's g1 of x plus 1/2. Okay. This is the choice of cost function has been restricted a little bit, and my system had to be control affine. But I'm going to say that's still a huge useful class of robots. Almost everything we write down is of that form. It's not a big deal. Okay, I'm going to take the gradient of everything inside that box with respect to u. And if you haven't done them a lot, you'll get used to it. But the gradients of the quadratic forms, it works out to be I get a 2, and then which cancels the 1/2. It works out to be u transpose r. Okay, and then plus partial j partial x, which again is potentially a complicated function of x. Okay, f2 of x could be a complicated function of x, but its dependence on u is simple. Okay, this gradient of this whole thing with respect to u is that, and I would like the gradient to be equal to 0. So I'm going to try to find the u for which that equals 0. And since r I've chosen to be invertible, it's easy. And I have to take a transpose to get this back in the form I want. But I get a negative r inverse. And then I flip this around with the transpose. The mechanics of that are not too bad, but I understand that you might just want to work through that, make sure you're happy with that. Okay. This is now the optimal u to take. And if I want to work with this as now a differential equation, I can actually get this differential equation, I can actually get rid of this hard to reason about thing, this minimizing over u, by just solving explicitly for the optimal u, sticking it back in that equation. I get a big complicated equation, but it's the hard, potentially nonlinearity from min over u is gone. Okay, so I can solve away u. Okay, and now here, this is really, the reason I really wanted to do this is I want you to understand in a deep, passionate way what this equation is telling you. Okay, so J is my cost to go. You should think of this as some potential well over space, which tells me how much cost I should expect to incur at each given state, right? It's a scalar function. It's a function over the space. What is this function telling me the best thing to do is in the continuous time, continuous function? There's a negative partial j partial x. First thing it's telling me to do is go downhill in the cost to go, right? But I can't necessarily go downhill directly in the cost to go because I got to work myself through the control limits, right? Especially if I'm underactuated, I might not be able to go straight downhill. F2 modulates my desire to go downhill into what I can actually, it maps me into the control space. This maps the going downhill into the units of u, tells me the u which goes downhill the fastest, okay? But there's one last thing I'm going to do to modulate it, right? I put a preference, by putting this in my cost function, this cost on u, I might have said that u1 is more expensive than u2, right? So this here takes my preference to go downhill, given my control authority, given my ability to go downhill, and modulates it a little bit to adjust for my preferences in u. Okay? So this is the story I want you to, when you see these equations here, and you're going to see it again, you might have seen it already in a linear case if you had a linear systems theory course, but when these things are linear, it's going to be a familiar set of equations if you've seen that. Okay? But this says, this says go downhill. This says but account for actuators, the actuator mapping. Right, map that desire to go downhill onto the input space. And then this says account for my preferences Okay, so this is really a very important idea, right? Is that the optimal control is going to find some cost function j. It's defined based on these partial equations, these partial derivatives. Okay. If I can find a function there, then my optimal action is to go downhill as fast as possible given these modulators. Okay, so borderline whether I have, I won't derive it here, but let me just, to put this in context, there's two things I want to do from here. One, I want you to see it in action with those assumptions in a problem we know, like the double integrator. And the other thing is I want to show you some code that exploits it. So I could show you the code. I'll put some code in the distribution so you can play with it. Okay, but let me just since I only have a minute left here, let me say if I were to do the double integrator here, if I take this system x double dot equals u, and I give myself a cost function, which is just the quadratic cost, which is the other one we used. Okay, and I'm going to have a quadratic in u, so this is control affine, and it has a quadratic cost on u. Now I'm going to just conjure this, because that's the point. If I'm just going to, now I'm trying to convince you that this is optimal. I'm going to give you a function j. I'm going to say that if you plug in this equation, and I'll leave it as an exercise because I don't have time to do it myself. I'm just pulling that out of thin air for now. I tell you, if you take the partial derivatives, stick it into that equation, look at the minimizing over u, okay, you're going to find two things. You're going to find the optimal controller is a simple thing. It's negative q minus square root of 3 q dot, okay? And that this thing satisfies the conditions for optimality. And I forgot to name them for you. Sort of one of the most important. This equation here that I've written down before, this min over u, gxu plus partial j, partial x, f of xu. This is super important. It deserves a name, right? This is the Hamilton-Jacobi-Bellman equation. That's a big time name. It's got a lot of important people on it, right? Some people call it the Hamilton-Bellman-Jacobi equation, but Bellman was alive in the 60s, and Hamilton and Jacobi are much, much older, so they definitely get to go first. I think in my book, that's not cool. You don't put that yourself in between Hamilton and Jacobi. Okay, this is the extremely important equation. We'll come back to it again. All right, but my claim is that if you stick that in, and you'll see something very simple out, and just to connect back. Right, so if I were to if I run that solution I already showed you, you're going to see that this thing does, in fact, there's two things to note about what I just wrote, right? The cost to go function is a quadratic function of q and q dot, and the optimal controller is a linear function, and you'll see both of those here in the solution. That turns into a linear function of state, and this thing converges on a quadratic function. Okay? Excellent. Next time we're going to do acrobats, cart poles, and quadrotors using all these tools. I'll see you then.